Okay, so that video was generally on the vision of Web3 and what the Web3 movement is all about. Now I'll go into currently the Web3 Foundation's main project, which is Polkadot. And Polkadot can be thought of as a next generation or a third generation blockchain. If you view the generations roughly as Bitcoin, Ethereum, Polkadot. So Polkadot enables two main features. Okay, cool, I have my slides. So it enables two main features, and those two features are interoperability between the chains that connect into Polkadot and shared security between these chains. So I'll go into more of the interoperability aspect with this presentation, but also try to cover the basics of the architecture and how Polkadot works. So Polkadot is a network that connects and secures blockchains. So it's built on Substrate, and the idea is that a chain that is built with Substrate will be able to connect into Polkadot. This is a visual of kind of how the Polkadot architecture works. Right now it might look a bit arcane and might not make much sense, but I'll try to break it down, and hopefully after I break it down, I'll show this image again and it makes a little bit more sense. So in general, the Polkadot approach, so Polkadot is a blockchain. If you're not super familiar with what a blockchain is, a blockchain really is just a chain of blocks. But what does that mean? So a blockchain is a state machine, and a block is a complete transition of that state machine. And blocks contain transactions, and each of these transactions are one transition in that state machine. And then the blocks are the complete transition. So you can just view a blockchain as a state machine, and each block is a new transition to that state machine. So generally how the Polkadot architecture looks like is a relay chain, and this is the kind of central Polkadot chain, and then what are called parachains, which is short for parallel chains, and these are the chains that connect into relay Polkadot. Chain, and this is the so just the pieces of the Polkadot architecture. We have the relay chain, the validator, who is securing the Polkadot relay chain, the parachain, which is a chain that connects into it, and the collator, which is the full node for the parachain that is producing blocks for the parachain and giving those blocks to the validator, who is then verifying the state transitions. And then the last piece, of course, is the block. So this is how it fits together. I think I kind of covered this, but just to clarify one detail, all of the parachains connected into Polkadot all have the same security of the entire Polkadot validator set. So Polkadot is a proof of stake protocol with finality. So it uses a consensus called Babe Grandpa. And Grandpa is the finality gadget of the Polkadot blockchain. So what this means is that the entire Polkadot network or the Polkadot system has a shared state. So each of the parachains have the same amount of security as the entire network. And the whole network performs state transitions as a whole. So the parachains have their state transitions, but then they report those transitions to the Polkadot validators, and Polkadot produces blocks as an entire system, as a shared state system. So hopefully this visual looks a little bit less confusing. So how does interoperability work in Polkadot? So Polkadot uses what's called the ICMP protocol, and that stands for interchain message passing. What it allows is for parachains to send messages back and forth to each other. Going a little bit deeper down, what this means is that each parachain will maintain both an input and an output queue of messages. And when they perform their state transitions, so when they produce a new block, they will read their input queue and execute all of the messages that are waiting to be executed. And then the validators can verify that these messages were indeed executed in this new block. Importantly, the messages do not go on the relay chain. The relay chain validators only verify that the messages were included in the parachains. So ICMP kind of talks about how messages go in between parachains, but it doesn't say what these messages are actually doing. And kind of the proposal for that is called spree. So spree is the shared protected runtime execution enclave. And breaking this down, what it is it's pieces of logic. So kind of similar to, you'll be learning about substrate modules, kind of similar to that idea where they're a module, but they're definitely a different thing. They're just a unit of logic. So something that does something. And these do live on the relay chain, and parachains can either opt in or opt out of a spree module. And the benefit of using spree modules is that the code will be identical across parachains, so that if you send a message to a parachain hitting a specific spree module, you know exactly what that'll execute in a trustless way. You only have to trust the validators of the Polkadot relay chain, and as a parachain, you're already doing that. So yeah, so it means that the interchain message passing is trustless between the parachains. So that's one aspect of the interoperability. The other aspect of interoperability are bridges to external chains. So here's an example. This is the kind of a similar diagram I showed earlier of the parachain, but this time it's bridging to an external chain. And in this example, I use Zcash. So the idea is that a parachain will be used as a consensus interpreter to the external chain. What this means is that basically the parachain will be a light client to this external chain. So it uses the bridge relay model. If anyone's familiar with BTC relay in Ethereum, it's a very similar idea. But it involves custodial actors who put up some stake on the Polkadot parachain and then operate a multisig on the bridged external chain. So people can give their external assets to these custodial actors, and if they try to run away with the money, we can take their stake from the Polkadot parachain. So you might lose the Zcash, but the idea is that you'll get the equivalent amount of dots in Polkadot. The other actors are the bridge relays. So this is the off-chain actors who are relaying the headers from the external chain into the Polkadot parachain. And this is necessary to do light client verification of transactions that were included in the external chain. And for a more detailed write-up, I provided a link, and I'll share the slides on the meetup page. And this just talks about how the constraints and what we'll be able to do with parachains for each of these external chains. So for Bitcoin, because the header size is really small, it's 80 bytes, probably one parachain slot can bridge to Bitcoin and all of the Bitcoin forks. So Bitcoin Cash and all of the rest. Ethereum, it's a bit more complicated because you want to do, they have larger headers, and you also want to do, you also want to verify things that aren't in the state tree, but are in the receipt tree, like the event logs. So like transfer logs, stuff like that. And Zcash is pretty similar to Bitcoin, but it only works with the transparent Zcash addresses so far. So about Polkadot implementation, there was a series of 8 POCs. So far the POCs 1 through 4 have been implemented. Currently POC 5, which brings interchain message passing and more stuff to do with parachains, is being worked on, as well as Cumulus, which is the extended library to Substrate, which will allow a Substrate chain to be connected to Polkadot as a parachain. And then in the future, before the Polkadot launch, there still needs to be implementation of validity and availability. And this is more complex stuff to do with erasure codes and stuff like that. But in parallel, a lot of teams are working on just tooling and additional applications around the Polkadot ecosystem. So Web3 Summit, that's where the documentary was filmed. It'll be happening again in August next month. And Kusama. So Kusama was announced earlier this week. It's a early version of Polkadot, which will go live a lot sooner. So it's not a test net, it's a canary network, and the name canary comes from the idea of canary in a coal mine. So miners would put a canary in the coal mine to see if the mine was poisonous or would kill you. So if the canary died, the miners knew to get out of the mine because there was some kind of poisonous gas in the air. So Kusama is the canary for Polkadot. The idea is that it'll test out the same incentives that are in the Polkadot network in a live environment. If you'd like to find out more, you can go to these links here. And that's it. If anyone has questions, I'd be happy to answer them.
Yeah, so I understood that we have a bridge between collators and external chain, right?
So, so in this diagram, the collators are kind of acting as the bridge relayers.
Okay, but that's basically.
But yeah, basically, yeah.
Why is that like this? Because as I understood, that collator just collects some transactions, right?
Mm-hmm.
Or intrinsic.
So yeah, so collators. So normally what collators do is they act as the full node for the parachain and produce blocks for the parachain. In this example, the collators are also acting as the bridge relayers.
Okay, but validators will validate this block, right? And
Yes.
Put this block, let's say, in, or somehow put this block in relay chain, right?
Yes.
But the relay chain is source of truth, right?
Yes.
And why collators are behaving like a bridge? Because from my perspective, validators should be like a bridge.
So there's two different roles. This diagram, I think maybe might be a little bit confusing, but there's two different roles that the collators are actually doing here. So it's not necessary that the collators for a parachain that is acting as a bridge to an external chain to be the bridge relayers as well. It's kind of a separate role, and collators could act as it. It probably would make sense if collators also did the bridge relaying, but that doesn't mean validators could do it as well. They wouldn't be required to in any way for their validation. But it also means someone who's neither a collator nor a validator could be a bridge relay. There are three kind of distinct roles. But otherwise, you were correct about the validation of the relay chain.
Hello, Logan. You mentioned that you have the same level of security in different parachain. Does it assume adversary corruption model? Because if you have some randomness when you divide some validators between parachains, this means that the malicious guy can corrupt particular validator, and it will be not the same level of security.
Yeah, so we do divide the validators up per parachain. So there's a couple things this means. One of the things is that it limits the amount of parachains that can be connected to Polkadot, depending on how many validators are validating Polkadot. So I think the number we're shooting for is between 5 to 10 validators per parachain at any time. And then the validators will get shuffled every hour, or possibly quicker. But yeah, in general, the number of validators will limit the number of parachains. Did that answer the question, or?
What about shuffling every hour? What is the source of randomness for this shuffling?
So it's a VRF based on, what is it based on? I don't have the details, but we have a VRF that one of the cryptographers at Web3 Foundation coded into the same library that we're using for Schnorr signatures.